Hello, everyone. Thank you for attending this seminar. How this will operate is that the presenters here will give you guys a few questions, and we'll give you a few minutes to try the problem on your own, and then we'll present it. So we will start with the first problem. So I'll give you guys a few minutes to try question 1, and we will begin. Oh, yeah.
Is this better? Yeah. Cool.
OK, so I believe we can get started with the solution. Or do you guys want more time? Good. OK. So in the question, we were in a scenario where we're at a pizzeria, and we want to purchase 2 pizzas, and we can select up to 3 toppings from a given 5. And we are allowed to have repeated toppings. So we are given a lot of information in this problem. So the best approach to this is reducing the problem to smaller parts. So we were given 2 pizzas. Let's start with just 1 pizza at first. So with 1 pizza, we'll find a number of total combinations, and then we'll move on to 2 pizzas. So we'll split this into cases. The question stated that we can get up to 3 toppings. So let's first do the easier scenario, 0 toppings. In this case, there's only one possible combination, because 0 toppings is just one possible combination. So in total, there is one possible combination here. Now let's move on to one topping. So we just want one topping on our pizza, and we can select from 5 toppings. In this case, since we only have 5 toppings and we just need to choose one, we will have a total of 5 choose one possibilities, or just 5. Now, this is where it gets a little bit more trickier, and this is when we have 2 toppings. So with 2 toppings, we could either have both of the toppings being different, for example, pepperoni and cheese, or we could have the toppings be the same, so double pepperoni. So we'll split this into 2 extra cases. One case where it is distinct, and if the toppings are distinct, we just have 5 possible toppings, and we want to choose 2 of them. So in total, 5 choose 2 toppings. And if they are the same, then we'll just have double toppings, so double pepperoni or double turkey. So in that case, we just do 5 choose 1. Is everyone following along so far? Okay. Now we're at our last case. The maximum number of toppings we can have in a pizza is 3 toppings. So the first scenario is if all the toppings are distinct. In this case, we have 5 possible toppings, and we just want 3 different toppings. So in total, 5 choose 3 toppings. Now, the second case would be 2 toppings are the same, and 1 topping differs. So in this case, we have 2 different toppings that are possible. One of them, well, 2 of them would be the same, and the other one would be different. So we can essentially treat the 2 toppings as just one singular topping here. So the number of ways we can choose one of these toppings double times, so we can have double mushrooms, for example, is 5. Now we have one option left, one topping that differs from the previous topping. In that case, we already used up one of the toppings for a double topping here. So we're left with 4 options. So 5 times 4, which is just 20 possible combinations. And finally, in our last case, I will write it down here. All the toppings will be the same this time. And it would be the exact same as how we did it with 2 toppings and 1 topping as well. We just have triple toppings. So in that case, we could have triple mushrooms, triple ham, triple turkey, and so on. So we would just have 5 choose 1. So we add up all these numbers, and we will get and the total sum of this would be 56. So in total, there are 56 possible pizzas we can get. But the question asks us to get 2 pizzas. So we want to find 2 pizzas, and we're given the number of combinations of one singular pizza is 56. So a common solution to this problem, well, I was going to say solution, but a common thing students write in this problem is the answer would be 56 times 56. The number of pizzas you can select the first time, there's 56 combinations, and the second time, also another 56 combinations. Yeah, let me just. So can anyone tell me what an error could occur here if we just do this 1 pizza squared? Yes?
Can you explain the ones where you have
Toppings are the same?
2 toppings.
2 toppings are the same. So this one here?
No, 5 times 4.
Oh, 5 times 4. OK. So in this case, so let me just label it here. 2 toppings are the same, and 1 topping differs. So let's say that we choose our 2 toppings to be turkey, for example. Then our final topping that differs cannot be turkey. It has to be either ham, mushrooms, cheese, or pepperoni. So we first select the topping that appears twice. We are given a case 2 toppings appear the same. So we select out of the 5 options which one appears twice. Then we're left with 4 options, and the final topping has to be different than the first topping that appears twice. But there are only 4 options left. So we have 4 possible different toppings that are singular. So in total, 5 times 4 toppings. Does that make sense? OK. So back to here, where we have this case being 1 singular pizza, and we're trying to get 2 pizzas here. Can anyone tell me the error of what could occur if we just do 56 times 56? OK. So the problem of just doing this is because if we're given, for example, let me just scroll up a little bit, a pizza which is just turkey, and a pizza that is just mushrooms, this could be our first pizza, and this could be our second pizza. But when we do 56 times 56, we could also have our first pizza being mushrooms, and our second pizza being turkey. The problem that arises here is that even though the ordering is different, when we buy 2 pizzas, we do not care of the order of the pizzas. A turkey pizza and a mushroom pizza is the exact same as a mushroom pizza than a turkey pizza. So we can't do 56 squared. So this approach is wrong. What we do is we first check if both pizzas are different. If that's the case, then we just select 2 pizzas of the 56 possible pizzas. And we're left with 56 choose 2 possible pizzas. But we have to also account for the cases where the pizzas are the same. So for example, I got 1 cheese pizza and another cheese pizza. In that case, there are 56 possible pizzas, and one of them appears twice. So we just add another 56. So in total, we have 56 choose 2 plus 56 total pairs of pizzas that we can purchase. Does anyone have any questions?
Why did you add 56?
The reason why we added 56 is because the pizzas could be the same. We could, for example, have a cheese pizza and another cheese pizza. So we already get all possible combinations. So there's a total of 56 possible singular pizzas. But we could get twice of them. So we just had to add 56 again. Does that make sense? Yeah.
Why don't we just divide it?
OK, so another question is, yes, you're saying 56 squared divided by 2?
Yes.
OK, so the problem with 56 squared divided by 2 is that although it accounts for the cases where if we have a turkey and mushroom pizza, for example, if we divide that by 2, it's a mushroom and turkey pizza. But the problem that arises here is in our count of 56 squared, we will have pizzas that appear twice or the same. For example, cheese pizza and cheese pizza. So that only appears once in the count of 56 squared. If we divide it by 2, we'll get 0.5 of a count, which doesn't really make sense. So if we want to divide by 2, we have to remove all the cases where they are the same pizza. Okay, does that make sense? OK. Any further questions? Yeah?
I got two questions. First, for the 3 toppings case,
Yeah.
why don't we consider 1 topping being the same and 2 toppings different?
So you're saying, can you repeat that topping?
Yeah,
Sorry?
for the 3 toppings case,
Yeah.
you only mentioned 2 toppings being the same and 3rd topping is different.
Yeah.
But why don't we consider 2 toppings different and the 3rd topping is
OK, so with 2 toppings being different, the third topping, the third topping is either the same as one of those 2 toppings. In that case, it will just be 2 toppings the same and 1 topping differs. Or the third topping is different than the first 2 toppings. In that case, it's just all distinct. OK, yeah.
my mouth messed up. The second question is that why when we add the 2 cases together, the first case is 56 choose 2. Can you explain that?
OK, so in total we get the number of singular pizzas we get are 56, right? So we will have 56 total pizzas, and we want to choose 2 of them to get all the possible different pizzas. So for example, if we have a turkey pizza and a ham pizza, we want to choose 2 of those pizzas in the end. And the reason why we add 56 is because if they're the same pizzas, it's not included when we do 56 choose 2. Yes?
I wanted to ask if it will be possible to write it as the sum of exponents, for example, by cases, but to do it in terms of, for example, 1 plus 2 times 5 plus 2 times 5 in the power of 2, then 2 times 5 in the power of 3.
So you're saying like you rewrite 56 as sum of exponents, or?
No, I meant like without using like 5 choose 2, 5 choose 1, like as the same as like slots. For example, for toppings, there are 5 possible options, and each option is independent. So that's why we multiply all of them and then do it by cases where we can select up to 3 toppings.
So you're saying if we have, for example, 3 toppings, why don't we just do 5 times 4 times 3? Or is that?
No, for example, if we have 3 toppings, why don't we do it 5 in the power of 3?
5 in the power of 3. So what happens here is that, for example, if I have a pizza, do I have space here? Yeah, OK. Let's say I have a pizza that has turkey and ham. So let's just say it's 2 toppings for now. So you're saying that this would be 5 squared, like possible for just 2 toppings, not 3 toppings, right?
Yeah.
So what happens is a similar case to this. We will also have ham and turkey. But do we really care about the order of toppings in a pizza? A pizza with turkey then ham is the exact same as a pizza with ham then turkey. So 5 squared, you have to account for the cases where essentially order doesn't matter.
If we divide it by 2, would it?
You could divide by 2, but then we get the, he mentioned earlier about the similar thing with the pizzas. There could be the same toppings as well. So we could have turkey and turkey. And that will be counted 0.5 times. So yes, it is possible to do it that way, but I think it's a little bit more complicated. But as long as you get the correct answer in the end, that'll be it. Yeah. Okay. I think we spent a lot of time on this question, so we'll move on to the next. I think I'll just present the solution right now, and the next problem I'll give you guys some time to try on your own. So for this question, we're given a word problem. John went to the groceries. He bought at least 2 apples, 0 oranges, and at most 15 bananas. And in total, he ended up buying 20 fruits. And the question asks us to find the number of combinations of fruits John can get. So let's just define some variables. A equals apple, O equals oranges, and B equals bananas. So we are given that the sum of all these fruits is equivalent to 20. Just to be clear, this is an O, not a 0, just to clarify. So I'll just, and we're given certain restrictions with each of these variables. A is greater than or equal to 2. O is greater than or equal to 0. And B is between 0 and 15. Even though it's not explicitly mentioned that B is greater than or equal to 0, we cannot have a negative amount of fruits. So we can say 0 is the lower bound. And yeah. So we want to find the number of solutions to this equations with these given restraints. So this is what you saw in this Monday's lecture is very similar to stars and bars. But the problem here is that we're given these constraints that make the problem annoying to solve and not standard to use stars and bars in. So we had to somehow force our way to make this equation into an easier equation that we can use stars and bars in. So in tutorial, you were shown that if you had a equation a1 plus a2 plus ... all the way up to an, and that's equivalent to k, and each ai is greater than or equal to 1, then the number of solutions for a1, a2 ... an, and oh yeah, I should have said this earlier, every variable here are integers. So the number of solutions here would just be k minus 1 choose n minus 1. This was shown in tutorial. Now, if we can reduce the problem a plus o plus b equals 20 into a problem like this, we can easily apply stars and bars. So with this equation, a plus o plus b, we can make some substitutions here. So a can be equivalent to a1 plus 1. Similarly, o can be equal to a2 minus 1. And we're given a tricky scenario here with bananas having an upper bound, which is not something that we're used to. We have been dealing with lower bounds so far. So how do we get rid of this upper bound? Well, we can split the problem in two. The first problem, the same equation, but this time we do not have an upper bound for b. So in this case, we substitute our variables. So b will also equal a3 minus 1. In this case, we would have a1 plus 1 plus a2 minus 1 plus a3 minus 1 equals 20. So in the end, when you isolate for the variables, you would have a1 plus a2 plus a3 is equivalent to 21. And we defined our ai to be greater than or equal to 1. So can anyone tell me how many integer solutions are here when ai is greater than or equal to 1? a1 plus a2 plus a3 equals 21. And each a1, a2, and a3 are greater than or equal to 1. Okay, so we plug in this formula here. So 21 minus 1 is 20, and we have 3 variables here. So 3 minus 1 is 2. So in total, this equation here has 22 solutions. Now, the second case is when a plus o plus b is equal to 20. Same restrictions for a and o, so I'll just repeat that here. But this time, I will get b greater than or equal to 16. So, oh, sorry. So this equation here, we do the same variable substitution. a1 plus 1 plus a2 minus 1 plus this time a3 plus 15. Because each ai is greater than or equal to 1, so we need 15 here for 16 to work. So this is equivalent to 20. When we isolate for the variables, we would have a1 plus a2 plus a3 equals 15. Sorry, 5. So we use the same formulas shown below, shown above. K minus 1 choose n minus 1. So we would have 4 choose 2 solutions. So why did I separate these into 2 different equations here? This is because if we subtract the number of equations from 2 to 1, so the solutions to 1 minus 2, we get every solution that has b that's greater than or equal to 0. But since we subtracted that from all solutions that have b greater than or equal to 16, we're left with everything that's in between, from 0 to 15. So therefore, when we subtract these 2 equations, we have all values that are greater than or equal to 2 for a, greater than or equal to 0 for o, and b is in between 0 and 15. So we would have, in total, 20 choose 2 minus 4 choose 2 solutions. Does anyone have any questions? Yes? Sorry? Yeah, so let me just use something in the bottom page here. So the reason why I subtracted equations 1 and 2 is because in equation 1, we are given these restraints. A is greater than or equal to 2, O is greater than or equal to 0, and B is greater than or equal to 0. So in total, we have all solutions in equation 1 where bananas are greater than or equal to 0, oranges are greater than or equal to 0, and apples are greater than or equal to 2. Does that make sense so far? So in equation 2, the reason now we define b to be greater than or equal to 16 instead. So same restraints for apples and oranges. So with these restraints, with b greater than or equal to 16, we have all solutions that have bananas being greater than or equal to 16. We have more than 15 bananas here. Does that make sense for equation 2? So when we subtract these two, if we just draw a number line, for example, in 1, we have all b's being greater than or equal to 0. So this entire number line. But in equation 2, if we define 16 here, we have all solutions from here. So this is equation 2. If we subtract these two, everything here gets eliminated. So we only have the values from 15 all the way up until 0. Does that make sense? Okay. So any more questions? Yes?
How could you decide that A would be A1 plus 1 and O would be A2 minus 1?
Okay. So the reasons why I chose certain symbols, for example, A is equal to A1 plus 1 and O is equal to A2 minus 1, is because of the restraints here. So recall how I said in this equation, if we have this equation of this form and each of the variables with the subscripts in A are greater than or equal to 1, then the number of solutions here is k minus 1 choose n minus 1. So with these variables, I can't use this formula because this is greater than or equal to 2, this is greater than or equal to 0, this is a range value from 0 to 15. So if I can somehow make these into a different equation where all of these variables are greater than or equal to 1, I can use this formula. So since we know that A is greater than or equal to 2, we can rewrite this as A is equal to A1 plus 1. And therefore, since A is greater than or equal to 2, let me rewrite it here. Yeah. A1 plus 1 is greater than or equal to 2. Therefore, A1 is greater than or equal to 1. So therefore, I have one variable here. Similarly, with A2 minus 1, this is greater than or equal to 0 from oranges being greater than or equal to 0. So if I add 1, is A2 greater than or equal to 1? The reason why I made these substitute these variables in is to get an equation of this form. Does this make sense? Okay. Yes?
Are we choosing specifically the restraints of AI greater than or equal to 1 just so we kind of know the formula off the top of our head and to count everything is that way?
Yeah.
Okay, good. Thank you.
Any more questions before we move to final counting question? Yeah. So I'll give you guys a good a few minutes to solve this problem, and then I'll take it up. Okay, I'll take up the problem now. So the question was asking us if each xi is a natural number, meaning that it's a positive integer, find the number of solutions of the tuple x1, x2 to x10 such that the sum of each of these values is less than 100. So here again, this is very similar to stars and bars. The only problem is this sign here. This is a less than sign. We want an equal sign to use stars and bars. So we had to somehow manipulate this equation to get us a stars and bars form. So what we can do is a very slight trick is that we can add a value here. So if I add these up until x10, I add a value called y, such that this will equal 100 no matter what, and y will be greater than or equal to 1. So the reason why I can do this is because we're given that this value here is less than 100. So the sum of x1 to x10 is less than 100. So if I add any value to it that is a positive integer, if this is equal to, for example, like 97, then we can make y to be equal to 3, and so on. So we can use stars and bars here because we're given that xi is also greater than or equal to 1 from it being a natural number. So we have the form k minus 1 choose n minus 1. Our k is being 100, so we have 99, and we have a total of 11 variables here. So we can do 11 minus 1, which is just 10. So therefore, the total number of solutions for this inequality is 99 choose 10. Any questions? Yeah.
Yeah. So since the equation has to be less than 100, why can't we just equal the equation to?
Sorry?
Why can't we just set the equation equal to 99, like initially, instead of adding?
So you're saying we should set this to be equal to 99?
Yeah.
Yeah, that accounts for one subset of solutions, but likewise, this could be equivalent to 98. Or this could be equivalent to 97, and so on. Any other questions? No? Okay. So we will move on to induction now. So what is the time? Okay, guys. Okay. Oh yeah, sorry. The previous question, yeah.
I'll get 10 bars to note with 10 xi's, and I'll have a set of numbers, which is 1 to 99, and the 10 noted numbers. So we'll get total 109 numbers to choose the 10 bars of each to note the sum of all of these. So the intervals between the two bars represents xi, and the interval, like the first interval represents x1. The second bar represents x1 plus x2. The third interval represents x1 plus x2 plus x3. So that represents 10 numbers, and I can put it, so I'll get a total bigger solution than this. How would it?
So you're saying that you store, okay, so you have these 10 numbers here, and you're adding another 99 numbers, to, and what are your bars again?
Bars is the
Sum of
before this bar. It's like if it's bar of 3, then it's all the sum from x1 to x3.
Okay, so you're defining bars from the sum from x1 to xi. And
Yeah.
so
I would just like randomly throw it into the number set 1 to 99. So I'll have like total 109 numbers, and then just choose its 10 bars to be just. So that I can just like directly to control all of these sums less or equal to than 99. Because the 10th bar can only like represents like before in the interval of the 98 and 99. So there's like 99 intervals with 10, like all other stuff.
okay, I'll try to understand your solution later. I'll present the next question. I'll come back to you later on. Okay. So with this question, we have an induction question, and we want to prove that 1 over n plus, oh, you guys can, yeah, okay. 1 over n plus 1 plus 1 over n plus 2 all the way up until 1 over 2n is greater than or equal to 1/2. So I'll give you guys a few minutes to try this problem, and then I'll take it up. Okay, I'll take up the solution now. So in an induction problem, our first step would be writing down the base cases. So with this particular question, we don't know how many base cases there are yet. But what we can do is right now just store the first base case, which is just n equals 1. And later on in our inductive step, if we're required to have multiple base cases, we can just go back to the base case. So with n equals 1, we just have 1 over 2, and it stops there, because n plus 1 is 2, 2n is just 2 when n equals 1. And we want to show that this is greater than or equal to 1/2. Well, this is obviously equal to 1/2. So this problem holds for when n equals 1. Now we will go on to our inductive step. Let me just add a little bit more space. So we should first write down our inductive hypothesis. So let's assume this inequality here holds for an arbitrary k. So it holds for n equals k. In this case, 1 over k plus 1 plus 1 over k plus 2 plus dot 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 plus 1 over 2k is greater than or equal to 1/2. Now, in our inductive step, we want to show this inequality holds for when n equals k plus 1. So we want to show that this equation here, 1 over k plus 2 plus 1 over k plus 3 plus dot 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 plus 1 over 2k plus 1 over 2k plus 1 plus 1 over 2k plus 2 is greater than or equal to 1/2. So when we're given an inductive step and we want to prove this statement here, we often have to use our inductive hypothesis. So we are given this statement, 1 over k plus 1 plus 1 over k plus 2 dot 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 all the way up until 1 over 2k is greater than or equal to 1/2. So can we add stuff to the inequality to make it of this form? So let's try that out. So yes? So 2k, you replace. Yeah, so I distribute. So technically 2k plus 2 is equivalent to 2k plus 1. Yeah, when you distributed properties, it's the same as 2k plus 2. Yes, so this is a chain that goes from n plus 1 all the way up until 2n. So technically right before this, there will be 1 over 2n minus 1. So in that case, that will be 1 over 2k plus 1. And so on. It's all numbers in between. The denominators are all natural numbers between k plus 2 to 2k plus 1. Does that make sense? Okay. So we want this inequality to be the same form as this. So let's get rid of 1 minus k plus 1 here. So let's bring this here. We would have 1 over k plus 2 plus dot 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 plus 1 over 2k is greater than or equal to 1/2 minus 1 over k plus 1. Now, we're very close. Now we start with 1 over k plus 2. We got rid of the 1 minus k plus 1. But we need to add these two terms here. So we will add them on to both sides of the inequality. So we have 1 over k plus 2 plus dot 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 all the way up until 1 over 2k plus 1 over 2k plus 1 plus 1 over 2k plus 2. And this is greater than or equal to 1/2 minus 1 over k plus 1 plus 1 over 2k plus 1 plus 1 over 2k plus 2. So this expression here is exactly as what we wanted here. Now, we're only left with this side as being the greater than or equal to side. So if we can show this statement here is greater than or equal to 1/2, we have shown the inductive step. So how do we show this? Let's try to simplify the terms with k's in the denominators. So this is equivalent to, as we can see, this is k plus 1. This is 2 times k plus 1. So we can rewrite this as 1 over 2 minus 1 over 2k plus 2 plus 1 over 2k plus 1. This is equivalent to 1/2 minus 1 over 2k plus 2 times 2k plus 1. Oh, sorry, plus. So this term here. So does anyone have any questions on how I got this term? No. Okay. So this term here has two terms in the denominator, 2k plus 2 and 2k plus 1. we already defined that k is a positive integer. So 2k plus 2 is a positive integer, and 2k plus 1 is a positive integer. And 1 over a positive integer, the product of two positive integers, is just a positive number. So this number, if we just call this number b, for example, we know that b is greater than 0. So this entire expression here would be greater than or equal to 1/2. So this is what we wanted here, but recall that when we did our want to show, when we took away the 2k plus 1 and 2k plus 1, we also had to account for the base cases in this scenario. So can anyone tell me what base cases we could, oh sorry, let me scroll up. What base cases we should include here? Extra base cases. One. Okay, so since we're taking away the 1 over k2 plus term, and we're adding on the 1 over 2k plus 1 and 1 over 2k 2 times k plus 1, we have to be careful about what happens when n is greater than 1. So when n equals 2, in this term, 1 over 3 plus 1 over 4, this term here is equivalent to 7 over 12, and this is greater than or equal to 1/2. Okay. Does anyone have any questions before I move on to the next induction problem? Yes?
Yes, can you go down, please?
Yes?
Yeah. How did we go from the, what did you say, even second equation, like the top one?
This one here?
Yeah, from left to right.
From left to right?
Yeah, how did we end up getting this is equivalent to this?
Okay, so you see this k plus 1 term here? And this is 2k plus 2, right? So essentially what I did here was multiply the numerator and denominator by 2. So I had the same denominator here, and if I just write this, let's write it here. This is just minus 2 over 2 times k plus 1 plus 1 over 2 times k plus 1. And that is just equivalent to negative 1 over 2k plus 1, which is this term here. Okay. We can move on to the next problem now. So I'll just take this up immediately. So I should have mentioned something in this problem. I'm going to let you guys assume that sum of the angles of a triangle is 180 degrees. So we start with our base case, obviously. N equals 3. In this case, if n equals 3, what kind of shape is this? If there's 3 sides? Yeah? Oh. Are you raising your hand? Or?
Yeah, why does the natural number n, why does it say that it's greater than or equal to 3? I don't think we've seen that notation come out.
Oh, okay. This notation here, if you haven't seen it in class, you can, it's essentially what it means is that whatever sign is here, you apply it to natural numbers. So this says greater than or equal to 3. So that means n is a natural number that is greater than or equal to 3. So, yeah. So with n equals 3, this is just a triangle. And I said in the statement, we can assume that the sum of the angles of a triangle is 180 degrees. So we can just, therefore, this is true. And we shown this holds for n equals 3. Now, let's move on to our inductive stuff. in our induction hypothesis, we will assume that for a k belonging to n greater than or equal to 3, that the sum of the angles is 180 times k minus 2. Now, we want to show this holds for a k plus 1 convex gon. So, want to show this holds for a k plus 1 convex gon. Now, forming a relationship between the induction hypothesis and the inductive step with the k plus 1 side shape and the k side shape is not an easy thing to think of. So the trick here is that let's assume we have a k plus 1 convex gon. So this shape here has k plus 1 sides. So how can I use the induction hypothesis to prove that the sum of a k plus 1 convex gon is just the value you plug in here minus 2? So 180 times k minus 1. The trick here is removing a triangle. So in a k plus 1 convex gon, let's take 3 adjacent vertices, A, B, and C. The 3 vertices will form a triangle. Now, if we just remove this triangle away from the shape, we would have removed 2 sides. So we removed AB and we removed BC. So we took away 2 sides. We took away 2 sides from a k plus 1 sided shape. So we're left with a k minus 1 sided shape. But when we remove the triangle ABC, we're left with a new side, AC. So when we remove this triangle, we took away AB and BC. We added a new side called AC. And if I just replicate this diagram here, forgive my attempted drawings of a shape, but when we took away this triangle, we're now left with a k convex gon here. So this is a k gon. And that's because we took away this triangle. Does that make sense to everyone? So what we did here is we know that this is a k gon, so we can use our induction hypothesis. Therefore, if I label the shape X, shape X has 180 times k minus 2, the sum of 182 times k minus 2 degrees. So how do we reconstruct this back? We just added triangle ABC back to get back our original shape, the k plus 1 convex gon. So we just do 180 times k minus 2 plus 180. And this is the same as 180 times k minus 1. And just a note, I didn't state this in this proof, but you should write down when you use the induction hypothesis for the exam. So I use the induction hypothesis here. So when I added back the triangle ABC here, I get 180 times k minus 1. And that's exactly what we wanted to show, because if we put a k plus 1 convex gon into this formula, we get 180 times k minus 1. So when we apply it back in this formula, it would be 180 times k minus 1. Does anyone have any questions? No? Okay. So I'll move on from this, and we'll go to the proof section. So you're given, is there a way I can zoom out a little bit? So I'll give you some time to attempt these two problems, and then I'll take them up. You're asked to prove or disprove both of these statements. Which question? The angon? Okay, we will take up later. Okay, yeah. Okay.
Okay, I can set this here also. No.
Yeah. I will.
So
Okay, when I finish presenting, I'll look at this. Yeah. Because I can't really concentrate right now because I have to explain this. Yeah, you can write it here.
is this simple way? So just
Okay, I'm going to take up the solution now. So you can still write here if you want, but I'll take up the solution now for these problems. Okay, do you guys want more time, or I'll take up the problems now? I don't see much people writing, so I will take up the problem. So let's look at the first question. Given that x, y, and z is a set of integers, so that this entire expression here, x squared plus 8z cubed, I'm not going to read all of it, but this entire expression, if this expression is odd, then x must be odd. So you guys in lectures were given a bunch of proof techniques, and doing exams when you're trying to solve problems, you should identify the best proof technique. So this is an implication, A implies B, and what happens is that we usually work with our left-hand side. But the problem here is that I assume most people will not want to start off working from this side. This expression here is much more simpler. It's just one term. This has 6 terms. So we want to somehow work with this side, but that's the right-hand side. So what we can do is use an indirect proof. So for this example, I will use proof by contrapositive. So let's write this as a contrapositive form. If x is even, then x squared plus 8z cubed times y, I'll just write down this expression, is also even. So, okay, much simpler to work with now, because now we can just say x is even and continue from there. Now, let's see if we can reduce the terms here. Let's check if there's any combined or like terms. So as we can see, 3y5 and minus y5, we can just subtract these two. So in the end, we get x squared plus 8z cubed times y plus 16x to the fifth plus 2y5 plus 12z11 times y15. Okay, so can anyone tell me what they see in these terms here? What do you notice about the coefficients? Yes? Yes, that's correct. So they're all even. The significance of this is because we want to show that this statement is even. So if all these coefficients here are even, we can replace this. If we take out a factor of 2, and we know that all of these terms divide by 2 because the coefficients are even. So if this is we can replace this with 2a, for example. So we just want to show that x squared plus 2a is even when x is even. So if what we know about x is even is that x is equivalent to 2y, where y belongs to the integers. So we can substitute that in with x, and we get 4y squared plus 2a, and we can factor out a 2 here, and that will become 2 times 2y squared plus a. And in the end, remember, we want to show that this entire expression is even. So this expression here is equivalent to x squared plus 2 times a. This is equivalent to 4y squared plus 2a, which is equivalent to 2 times this expression. But in the definitions of an even number, it's of the form 2, and we can substitute this as 2 times b. And this is our definition of an even number, where b belongs to the integers. So therefore, we've shown that if x is even, this entire expression is also even. And we show this by proof by contrapositive. So does anyone have any questions? Yeah?
Why is already defined to mean x is
Oh, my bad. I didn't even. Yeah, c. Why not? And c squared. Yeah, my bad, guys. So c instead of y. So now we can move on to the second question. So that the sum of any two composite numbers is also a composite number. Now, with this question, you wonder how to start off this problem. Well, intuitively, what you can do is that if you're given a general expression like this, yeah, you have your right hands up. A composite number is any number that can be written down. So if I have a number x, it can be written down as a product of a and b, a times b, such that a and b are both greater than or equal to 2. So another way to think of this is that it has a factor that is not 1 in itself. I think that's the easier expression to say this. But yeah, it's not a prime number. Prime number only has 1 and itself as factors. A composite number will have one more factor that is not 1 in itself as a factor of x. So intuitively, what you can try to do is try to find some counterexamples, because if this holds, because what we know about composite numbers is that since they're not prime, we can try a bunch of values. So let's say, what are specific values we know about composite numbers? What are specific properties? No, okay. So what we can try to do is a composite number, any even number that is not 2 is composite. So if we want to show a counterexample to this, let's not make our two composite numbers odd or even. Let's make sure that they're both not odd or even. Because what happens is that if we have an odd plus an odd, that becomes an even number. And likewise, if we have an even plus even, that becomes an even number too. So what we can do to reduce our search is find an odd composite number and an even composite number. So one such example would just be 4 and 9. 4 is composite because it has a factor of 2, which is not 1 or 4, and 9 has a factor of 3. So what happens when we sum these numbers up? 4 plus 9 equals 13. And is 13 a composite number? No, because 13 only has two factors, one in itself. So therefore, we sort of counterexample to this problem. We had two composite numbers, 4 and 9, and the sum is prime. It's not a composite number. So we have disproved this statement here. Okay. Any questions? No? Okay.
Thank you, Prithvi. All right, so hey everyone, my name is Malhar. I'm going to set things up. You can have a small break. You can hit the washroom. Try to get active again. Let's say I give you guys up until 25. We're going to start, and I'm going to be using the board. We will start with set proofs. We've seen this in lecture 3, right? We've seen set notation earlier in lecture 1, and then now we have set proofs. So I'll give you guys maybe a couple minutes to look at question 1 and understand what it means. If at any point you guys don't know what anything here means, just raise your hand, and I'll help explain it. Okay? Okay, it's been a couple minutes. I'm assuming everyone understands what the question is asking. Yes? Good. Okay, so I'm going to ask you guys what you think the answer is. Is this statement true or false? Yes.
I believe it's false.
Why do you think it's false?
Well, give a counterexample of,
some 3 tuples, A equals 1, 2,
Sure.
and then B equals 2, 3,
Okay.
and then C equals 3, 4.
Okay. And this is a counterexample how?
So A and B would share one element.
Mm-hmm.
So that makes
Which one?
set A and set B would share one element, which is 2.
Okay.
And then B and C would share one element, which is 3.
Okay.
And A and C would share no elements.
Ooh. Good. So we disproved this implication by showing a case where the left-hand side is true, but the right-hand side is false, right? And this is how you disprove implications. You give a counterexample. Okay, any questions? No questions? This was a pretty simple one. We can move on to the next one. I'll again give you guys maybe a minute or two to read the question, as well as think about what the answer is. Why is this tilted? Maybe this is better. Better? Cool. Okay, let's get started. So first of all, this question has something that you might not have seen before. It's called a power set. And a power set is also a set. It takes in as inputs some sets, and the power set of that particular set is the set of all subsets. So for example, if S is 1, 2, 3, then how many possible subsets are there? Well, your subset can either contain an element or not. So for whatever size it is, it's 2 to the power that size, because for every single element, you have 2 options. So for this, the power set would have size 2 to the power 3, which is 8. And I've actually gone through and written them out for you. You can see that every single element in this power set is a subset of S. And there's no element here that isn't a subset of S. Okay? Cool. So we now know what a power set is. What this means is if you have something of the form, let's say T is a subset of S, what this also implies is that T is a member of the power set of S. Right? If T is a subset of S, it must occur in the power set somewhere. But it's in elements. It's not a subset. Cool. Great, 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 great. Let's try and look at the first part, the first statement. Can someone, instead of all of that mathematical jumbo mumbo you have over there, explain to me in plain form English what that statement is? Just the top one. Yes.
The union of the subsets from set A and set B is in the subset of A union.
Yeah, basically correct. So this statement is saying if my set is either a subset of A or a subset of B, then it must be a subset of A union B. Okay? Do we think this is true? Do we think this is false? Can I get a raise of hands if you think this is true? Okay, quite a bit. A raise of hands if you think it's false. Okay, 1 or 2 people. Why do you think it's false?
Because if you say that like A has n elements and B has m elements, and the power set of A would have 2 to the power n elements, and power set of B would have 2 to the power m elements. So if you suppose that like A intersection B is 5, so basically that they're empty, right?
There's no intersection. We're doing unions here.
No, but I'm saying like suppose that they're disjoint, right?
A and B are disjoint.
Yeah, like suppose that they're
Okay.
disjoint.
So let's say A is 1, 2, and B is 3, 4. Okay.
So, I mean, like m does not have to equal n, but like.
Sure. 3, 4, 5.
Yeah.
Okay.
But you say that like so, p the power a, power set of A is basically the number.
Any subset of this.
Yeah, I mean the number of elements in PA would be 2 to the power 2, which is 4, right?
Right. Right. So that's totally fine. If A is of size A, small a, and B is of size small b,
Yeah.
then P, the power set of A union the power set of B, the total size of that would be 2 to the power A plus 2 to the power B minus 1. Given that these two are disjoint,
Correct.
right? Why the minus 1? Because both of them have the empty set. It's overcounted. That's fine. And on the right-hand side, you have 2 to the power A plus B, which is definitely greater than this. That doesn't mean that all of these elements can't be here, right?
Fair enough. Yeah.
But this is a really good insight, okay? And it might be useful for the second part. Okay, so the answer is that this is true. And the way we're going to do it is just by assuming the left-hand side and showing the right-hand side. We're going to convert the statement into something that is an implication. If X is a subset of A, or X is a subset of B, then X is a subset of A union B. This is exactly that first statement. Take some time and realize why this is the case. Now, does this seem obvious? If X is a subset of A or B, it must be a subset of A union B. If it isn't, where'd this new element that's neither in A union B come from? Okay? So this would just be trivially true. How? Well, you can do it by cases. Case 1, X is a subset of A. Well, this directly implies X is a subset of A union B, right? Just by the property of union. And then similarly, case 2, X is a subset of B implies X is a subset of B union A. Same thing, right? So in either case, you get this. Okay. So that's the first part. Any questions regarding this? No? Cool. Second part. Now, I would have given you guys an opportunity to express your thoughts on equality, but we've already been given a really good reasoning as to why this is probably false. Yes?
Can we prove that it is false using inclusion-exclusion principle?
To prove it false, the best thing to do is just give a simple counterexample if you're trying to prove it being false. Which means X is a subset of A. X is a subset of A union B. And if that's not the case, then X is a subset of B, and then again you have to show that X is a subset of A union B, both of which follow trivially from the property of a union. Okay? Cool. So a classmate of yours gave a very good reason as to why this must be false. What do we usually do to prove equality in sets? Yes?
We prove that one with subset the other, and vice versa.
And vice versa. So we've already proven that the left-hand side is a subset of the right-hand side. So if this statement is false, that means the right-hand side is not always a subset of the left-hand side. And we can give a pretty simple counterexample for this, right? Let's A be 1, let B be 2, and let X be the union of the two. What do we have here? We have X is a subset of A union B, which means that X is a member of the power sets of A union B. But as you can see, X is not a member of the power set of A, and it's not a member of the power set of B. Right? X is not a subset of A, which means X is not in the power set of A. Similarly, X is not a subset of B, therefore X is not a member of the power sets of B. Any questions? No? Cool. Just a quick question. Am I going too fast, or is this reasonable? Reasonable? Okay, cool. Great. All right. Well, that's it for set proofs. Our next question, or next set of questions, are PHP. I'll give you guys a couple minutes to think about this. Maybe a little bit more, if you guys request it. A couple things to keep in mind while you guys are thinking about this question. Friendship being mutual means if I am your friend, then you must also be my friend, right? So when I'm counting the number of friends I have, if I count you, you also have to count me, okay? Okay.
Sorry, I have a question.
Yes.
Do we have to assume anything because there are no assumptions, so we can basically say that like 20 people, like each of them can have no friend?
Yeah, that's totally fine. If all of them have no friends, pick any two, they both have the same number of friends, 0. Okay, all right, let's get started. What's the problem with this question? Can we apply PHP directly on this? What are the number of people? How many people do we have? 20. Okay. And what are the possible number of friends that a person can have? Starts at what? Starts at 0. It's pretty sad. But it goes up to what? 19. Great. Life of the party. Why can't we use PHP here? Anyone? We can't use PHP directly here. What's the reason? Yeah, we want the number, well, it's not less than, but the number of holes is equivalent to the number of pigeons. We can only apply pigeonhole principle when there are more pigeons than there are holes, right? Right now, this is also 20. So what happens if, every single pigeon goes in each of these holes? Well, there's a problem there. There's a contradiction in this particular case. What is the contradiction? Think about this. If every single person, let's say person A has 0 friends, B, and then so on, and what comes before T? S. Person S has 19 friends. Where's the contradiction? Hints? Take a look at these two. Sorry, what was that? I couldn't get it. It's what?
It is odd.
What is odd?
Sum of all threes.
No, that's not a violation. By the way, it's not odd. The sum from 0 to 19 is 19 times 20 over 2. Still even. There's a bigger contradiction.
Yeah,
Yes.
It's like the person with 19 friends would be friends with everybody else in the group.
Yeah.
But like you're saying there's one person with 0 friends. But
Mhm.
how is that if like one person's friends with everybody else?
Exactly. If person A has 0 friends, that means he's not friends with person S. But if person S is friends with everyone, then S is a friend with A. That violates the mutual friendship rule, right? So this can't be the case. So how are we actually going to show this? We show that this contradiction is why we can't have a pigeon in each hole, and usually that's enough. But I'll show an alternative way where you can break it into cases. Case 1. Let's actually define a few things. Let's define PI is the number of friends of person I, where I belongs to the set of 1 through 20. So case 1 is that P of I is greater than 0 for all I. What does this mean? Every person has at least one friend. In that case, the list of possible PIs is 1 through 19, right? And then you have 20 people, then therefore by pigeonhole principle, there must exist, actually let me write this down, by PHP, there exists 2 people, 2 distinct people such that P of I is equal to P of J, right? They have the same number of friends. Great, that's one case. What's another case? There exists 2 people, at least 2 people, such that all of them have 0 friends. If there's 2 or more people with 0 friends, you just take any of those 2. They have 0 friends. They have the same number of friends. Okay, so these are the easy cases. And then case 3, exactly exactly one person has 0 friends. Right? Without loss of generality, assume it's person 1. So P1 is 0, but for everyone else, it's greater than 0. In this case, because there is one person with 0 friends, what happens is that nobody can have 19 friends, right? List of possible number of friends. Is 1 through 18 for the rest of the people. How many are there except from person 1? 19 of them. And out of them, they can only have 1 through 18. Pigeonhole principle, there exists 2 people. I not equal to j, not equal to 1, because person 1 we already excluded, such that pi is equal to pj. Okay, this is a different way of proving it. The contradiction method is also just as fine. Okay, questions? No questions? Cool. Let's move on to the second PHP question. This was fun to make. I enjoyed it. Hope you do enjoy solving this. Let's move this up. Is there anyone here who doesn't know what tic-tac-toe is? No? Everyone's okay with tic-tac-toe? Oh, okay. So tic-tac-toe is a game that is played by 2 players. It is played on a 3x3 square. And then one player is zeros, and the other player is X. Sorry.
Yeah. Is it possible that like you basically like 9 places, right? Like
Yeah.
on the grid.
Yeah.
Like each.
Is this, are you trying to give a solution?
Yeah.
Okay, let's have you wait for that. Let me explain what tic-tac-toe is first. So then there's 2 players. Player 1 puts zeros on this grid, and player 2 puts X's on the grid. So for example, if player 1 starts, it's then player 2's turn, then player 1 starts, and it's player 2's turn, then player 1 starts, and then it's player 2's turn. The game stops when you can have a row or a column or a diagonal is all zeros or X's. Okay? And if it's all zeros, then player 1 wins. If it's all X's, then player 2 wins. Okay? All right. Is there anyone here that needs just a little bit more time to solve this? No? Okay, we can get started. Cool. So you wanted to.
Yeah. I was just saying that like if you have like 9 places, right?
Mhm.
Each place you can either put a cross or a circle, right?
Yep.
So like the total ways that you could possibly like play the game is like 2 to the power 9, because like you're multiplying 2 into 2 into 2 like 9 times, right?
Mm-hmm.
So-
That's sort of a subset method.
Yeah. So
Okay. This is not exactly correct. Because, for example, OXO and OXO in this other order are 2 different games. although they're the same in the count. Okay?
Yeah.
Cool. But you're on the right track. You do want to find a upper bound and show that that upper bound is less than 1 million. Okay? What's a better way to find this upper bound? Well, this is what we're going to do. Player 1 has 9 choices available. He could put his symbol on any of the 9 squares. So he has 9 options. Once that square is filled up, player 2 has 8 options. Then it's 7 options, and so on and so forth. So there's a total of 9 factorial ways a particular game can go. Now this is a very loose upper bound. Can someone tell me why this is not precise? Yes. Exactly, exactly. You can end the game. You don't have to play out until all 9 squares are filled. You can end the game as soon as 5 moves, right? So that's fine. This is still an upper bound, right? So total number of games less than 9 factorial. There's one more thing that can change. There could be 2 games that are identical in the steps, but still somehow different. Turns, players. You could have been player 1 or player 2 in that case, right? So accounting for that possibility, the total number of games is less than 2 times 9 factorial. Okay? Everyone understand why this is the case? Cool. Now we just have to show that this is less than 1 million. You can do this using a calculator, but the way I justified this was, let's actually write it out. 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. And now I'm going to do a few things that will increase this number, right? First of all, I'm going to take this 2 and 5 and just say it's times 10. That's fine. That's equality. So I can remove this 2 and 5 and instead just multiply by a 10. Additionally, I'm going to replace this 9 with a 10. Now I'm getting a number that's bigger. Fine. As long as we show that even this big number doesn't exceed 1 million. Or, sorry. This big number is still valid. We're still fine. Next, I will take these two, 3, 8, and 6, 4, and write them as 24 each, right? So now you have 24 squared. Whoops. Yeah, OK, that's fine. So now I can remove this. And basically, we have 9 factorial is less than this number, 7 times 24 squared times 10 squared. Furthermore, I will replace 24 by 25. It's still less than. OK? And then furthermore, I'll replace the 7 by an 8. It's still less than. And then if you actually do the math, this is 500,000. OK? So if 9 factorial is less than 500,000, then 2 times 9 factorial is less than what? 1 million. Great. That's it. That's the argument you need to make. Once you've shown that the total number of games possible is less than 1 million, if you've played 1 million games by PHP, there must be 2 games where you were the same player and you executed the same exact sequence of moves. It's the number of possible ways you can play a game. Player 1 has how many options? Where can he put a 0? 9 spots. Once that's filled up, player 2 has 1, 2, 3, 4, 5, 6, 7, 8. Then 7, then 6, then 5, and then 4, so on and so forth. OK, this was a very loose bound. if you look online, you can do a combinatorial analysis. You'll have to break it by cases. Number of games that end in 5 moves, 6 moves, 7 moves, 8 moves, 9 moves. You don't have to know this, but then the total is around 250,000. So even if I said instead of 1,000,000, 600,000 games, it would have still been true. Questions? Yes? Why did I multiply by 2? Well, you could have the same sequence of moves, but let's say both of us play the same game twice. But in one case, I'm 0, I'm the O's, and you're the X's, and in the other game, you're the zeros, and I'm the X's. Right? It's for players. So to play the exact game, you need to be the same. You need to have the same symbol, and you need to execute the same number of moves. Okay? Cool. We have maybe 15 minutes more to go through, so apologies for that. This final section is, well, the first question should be pretty straightforward. This is binomial coefficients, so this is regarding the binomial theorem and combinatorial theorems. I'll give you guys 2 minutes to do question 1. The hint is to use the binomial theorem. Okay, so we're going to start. Does anyone want to tell us how to do it? Yes?
So like if you expand summation, like every single time you increase I by 1, it like from like -1 to like 1. So if you add those two together, it will become 0.
Okay.
And if you like expand it to like n, like
Okay.
empty n, it will be like
Okay, what about the case where n is even? Then there's some middle elements that doesn't get canceled off. Then what? Wouldn't that make it non-zero? So for example, 4. Then you have 0, 1, 2, 3, 4. The 4 cancels out with 0. 1 cancels out with 3. What about the middle element? There's a simpler argument to be made. Yes?
We can use the binomial expansion formula.
Yes.
Over there. And the reason why is because we have -1 to the I, but there's obviously an invisible 1 multiplying it, which is the 1 to the n minus I. So the formula also is a plus b to the n.
What are a and b?
And a in this case we can choose to be -1, and then b we choose to be 1.
Yeah.
Then
Yeah.
1 plus 1.
Correct. So essentially we're going to be using this binomial theorem. Keep in mind that knowing what values you can use is important. So this is true for all natural numbers, which includes 0, and for all a comma b being reals. Okay? So this we've seen. Equivalently, I can say this. Why can I change the power? Why can I swap the exponent in these two cases? Why are they equivalent?
As you keep moving, like it's gonna like weighted by the time you reach the end. It's the same thing.
Yep, yep. Or more simply, a plus b to the power n and b plus a to the power n are the same. So if I were to swap b and a, this is what I would get. Exactly the same things. So now what I can do is I can substitute a equals 1 and b equals minus 1. And look at what I get when I use this second summation. 1 to the power whatever is just 1. We can just choose to exclude that. Minus 1 to the power I, and choose I. Great. So we have this side. And on the left-hand side, 1 plus minus 1 is 0. 0 to the power n is 0. OK. Questions? OK. If there aren't any questions, we'll move on to the last part. Make sure you understand the hints. If you don't, raise your hand. I'll give you guys a little bit more time, maybe 4 or 5 minutes to figure this one out. Okay, we're going to get started. Before we start, any questions? Is everyone comfortable with the summation notation? Does everyone understand what that summation means? It's 0 times n choose 0 plus 1 times n choose 1 plus 2 times n choose 2 all the way up until n. So it's n times n choose n. Okay? And we're going to do exactly what the summation tells us to do and expand it. Exactly what the hint tells us to do. So the first term, the 0 is just nothing, we can't expand it. Then we have n choose 1. Then we have n choose 2 twice. Then we have n choose 3 many times, 3 times. And then so on and so forth up until we have n choose n n times. Okay. What do we know about this? This is a very common summation. It's 2 to the n, right? Okay. This is important. Cool. This looks like half of a square, right? This looks like there's some part that's missing. If we look at the column, what's different from that summation and this column? What are we missing? Which one? No, let's just focus on this column. Just the first column, look at that summation. There's one term that we're missing here. Which term are we missing? Here we start at 1. We're missing 0. We're missing n choose 0. So if I had that extra n choose 0, this column would just be 2 to the power n. Correct? Similarly, if I had n choose 0 and n choose 1 over here, this column would also be 2 to the power n. So extending that idea, if I had this upper triangle as well, I would just have a bunch of 2 to the power n's, right? What would the total of this be? Can someone tell me how many columns we have in total? How many times do we add n choose n at the end in that summation? What's the last term of that summation? N times, right? N times n choose n. So there's n of these. So if I had this upper triangle as well as part of my summation, I would just have n times 2 to the power n, right? Because each column is 2 to the power n trivially by that. And then you have n columns. This is just for intuition. This is not how you will be solving this problem. Now there's one massive insight that we need here. What can you say about this bottom triangle, which is part of the summation, and the top triangle, which are these terms that we wanted? Look at the first and last row. That's fine. Every single row is repeating. Equivalence. Correct. N choose n is equivalent to n choose 0. Similarly, n choose n minus 1 is equivalent to n choose 1, and so on and so forth. So what ends up happening is you have this equality between each of these rows, right? So you have, for example, you have n choose n times. Then if you also had n choose 0, which is equivalent to n choose n times, that's exactly what you need. For example, let's say this was actually the complete one, and let's say it's just n choose 4. 1, 2, right? Then this is equal to this. This is equal to this. And there are 2 terms here. We wanted 2 more, which is also half. Even if there is a middle row, it's exactly half. The insight that we develop here is that this upper triangle is summation is equivalent to this lower triangle summation. Okay? Does everyone understand why this is the case? This bottom triangle that we have over there is equivalent to this top triangle that we just created in terms of its count by equality. What does this mean? We know that the entire square is n times 2 to the power n, and we know we can break it into 2 equal halves, and we only want to find the value of 1/2. So what's the value of that half? Just half of this. Divide by 2 is just -1 in the exponent, right? Now you have your answer. This is not how you're going to present it. This was for intuition. To present it, we have to express whatever we said here mathematically. Mm-hmm. 0. Whoops. 0 to n, I, n choose I. Okay. So another hint is, or another way to think about this is a summation, right? If you were to do the summation in the reverse order, would the value of the sum change? It would not, right? I'll get back to you in a minute. So this is what this summation looks like if you go from right to left, if you go backwards. Convince yourself that this is the case, that this is the same as that summation, it's just in a different order. What's the first element here? N minus 0, n times n choose n, which is that last element over there, and vice versa. So we know that these are actually equal. Okay? Add both of them together. I, n choose I, plus n minus I, n choose n minus I. All of this is in the summation. One last trick. One last thing we need to merge everything together and get a simpler answer. What is it? Yeah. N choose n minus I is equal to n choose I. Right? It's a combinatorial property we know. 10 choose 2 is the same as 10 choose 8. Right? Okay, I plus n minus I is just n. N is a constant, you can take it out. N summation I equals 0 to n. N choose I. Okay. What's the last step? We have this summation. Well, we still need to simplify this summation, which we know is 2 to the power n. So we have a plus b. So there's two things. We have a equals b, and we have a plus b is n times 2 to the power n, which implies the summation that we want. A is n times 2 to the power n minus 1. Okay? Cool. Any questions? No? Okay, if you guys don't have any questions, there's one thing that I do want to add. There's this question that we didn't get to cover because of its difficulty and due to time constraints. Please take a photo of this and try to solve it. If you can't, you can just look on the art of part. You can just search AOPS and you'll find the solution. Okay, but try to do it yourself. It's a pretty neat induction question. Cool. That's it for this review seminar. Thank you all for taking the time out of your day to attend. And keep an eye out because we'll be doing this for the upcoming the second term test or the second midterm, and also for the final. Not just for this course, but for many of the courses around here at the CMS departments.
Thank you. I have a quick question.
Yes.
You see the end summation final step?